Today we're going to discuss work and energy. Energy is like the single most important topic in physics. It can explain a great deal of what goes on in nature. And in fact, when you try to understand nature and you try to figure out what are the rules, the number one rule that Mother Nature obeys is conservation of energy. Work is related to energy because work is how energy gets transferred. Or you could think of it as another form of energy. But either way, whether you think of it as a scooper that scoops energy out of one bucket and puts it in another, or a bucket of energy itself, doesn't matter. So the first thing we're going to define is that there are three terms, actually four terms. We are going to be talking about work, which is doing something. We're going to be talking about kinetic energy, which is the energy of motion. Anything that is moving has kinetic energy. We're going to be talking about potential energy, actually in the next chapter, which is stored energy, or you could think of it as the energy of position, energy that something has because of where it is. And then finally, power, which is the rate of work or energy. And this last one is actually very important to human beings. We are creatures who live with a constant flow of time. They talk about time being the fourth dimension, but it's not really, because we don't control it. You can't move back and forth in time. But we are always concerned with how much time does something take. So the symbol that we're going to use for work is going to be a W. The symbol we're going to use for kinetic energy is going to be a K. So far, so good. The symbol we're going to use for potential energy is an uppercase U. Yeah. And the symbol we're going to use for power is an uppercase P. And all three of these are going to be measured in a unit called joules, abbreviated with the letter J. This one, however, because it's a rate, is going to be measured in joules per second, which is also known as a watt, abbreviated with a W. Okay, now let's get right to it. The recipes for these things, the recipes for how to calculate these things. And I'm not going to give you the recipe for potential energy because, again, we're going to cover that a little later. Work is basically a force times a distance or displacement. So work equals force times displacement. However, that force has to be causing the displacement. So not only do you have to demonstrate causality, in other words, is that force at all related to the process that you're observing, but also if there's a misalignment, then we need the part of the force that is in the correct direction. So a lot of people do that by saying force times displacement or distance times the cosine of the angle between the force and the displacement. These two are vectors. Work is a scalar. And this is actually what they call a dot product in the world of vectors. Okay, kinetic energy is got one recipe, 1/2 of the mass of the object times its velocity squared. Later we're going to discover there's another quantity that has mass and velocity in it. It's going to be called momentum. But this recipe has mass, 1 helping of mass, and 2 helpings of velocity. Velocity is very important. And power is going to be work divided by time, or any other kind of energy that you have divided by time. All right, so you watched the short video about this, and they talked about a situation in which some poor soul was pulling a block across the floor, and we're going to ignore friction for now, and this block was being pulled at some sort of angle. Let's call it 12 newtons at a 20-degree angle, and this block furthermore is 5 kilograms, and we're going to move it from here, 0, to over here, 10 meters across a room. So how much work is being done? Okay, the very simple calculation is that the work being done is the force you're exerting times the distance it's going to move times the cosine of the angle between them. All right, the force being used is 12 newtons. The distance being moved is 10 meters, and we need the cosine of the 20-degree angle between them. So 12 times 10 times cosine of 20 equals 113 when you round up. 113 joules of work have been done. If it takes 10 seconds to do so, what is the power? How much power have you exerted? In other words, what size electric motor would you need to get this particular job done? Power is just a rate, so we take our 113 joules and we divide it by the 10 seconds, and we get that that's 11.3 watts. So to drag this thing across the counter or the room or what have you, you would need to use 113 joules of energy, and you would be developing or consuming, or whatever word you want to use for power, 11.3 watts. We can take this just a little further if we'd like to, and but I just want to point out that this is a scalar quantity. It doesn't have a direction associated with it. Just want to let you know about that, okay? This is also a scalar quantity because if you divide a scalar by time, which is a scalar, you get a scalar. So where does this energy go? You, in pulling this thing, have lost 113 joules from your body somehow. You're more tired. Your chemical stores of energy have been used up. Where did it go? What's going on with this thing? Well, if we were to figure out what happens to this thing, we would say that, okay, so we exerted a force, and the force was 12 cosine theta. That force leads to an acceleration, and the acceleration plus the distance will lead to some sort of velocity. So let's figure out that velocity. So the force exerted was 12 cos theta, and if we take the 12 cos theta and divide by the 5, 12 cosine 20, so force divided by mass equals acceleration. Then we divide by 5. Okay, so we're going to have an acceleration of 2.26 meters per second squared. Okay, good. Now we know that we have a position of 10 at the end of this thing, maybe a starting velocity of 0. We want the final velocity. We have an acceleration of 2.26. Oh, this is very interesting. This is very interesting. We have a time. I said 10 seconds, didn't I? But that's not really going to be the time. That's interesting. I just made 10 seconds up on that last thing. So we're going to have to use the no time equation. So VF squared equals VI squared plus 2AX. VF squared is going to be 0 squared plus 2 times 2.26 times 10. So we need to multiply our 2.26 by 20, and we're going to get a velocity squared of 45, and we're going to take the square root of that number, and we're going to get a velocity final of 6.7 meters per second. All right, well, I said earlier that the kinetic energy formula was 1/2 mv squared, so 1/2 of 5 times 6.7 squared, or 1/2 of 5 times 45. After all, we just took a square root over here to get this, and so we'll put this in here. Okay, hold on. I got to. And this rounds up again to 113 joules. Now, that cannot be a happy accident. There must be something going on here, and it does reveal to us the most important thing of all, which is known as the work energy theorem. Work equals the change in any kind of energy. And since the energy we're changing here is the kinetic energy, the work done equals the change in kinetic energy. Work changes energy. That deserves, oh gosh, how about pink? This is kind of a specialized version of the more general conservation of energy, which says that energy can neither be created nor destroyed. It can only change forms. And here it's changing form from work into kinetic energy. That's if you think of work as a type of energy. The other way to think of work, as I said, is that work is the scooper or the mechanism by which energy is transformed. And so that means that the amount of work done came from some other energy, and work is the bridge by which the energy moves. So you could think of it as the fact that inside your body you have chemical energy. Oh, did I leave enough room? Yeah, barely. And that work done by you changes some of your chemical energy into kinetic energy of the box. So work is this process. That's a great way to think of it. Okay, that's an introduction to work and kinetic energy. We'll do a little more in a few minutes.